Okay, so trig ratios. I'm going to show you guys. There's a whole. If you've looked at, you're in the process of scheduling classes, so you probably looked at the course guide and all that stuff. There's a class called, or half a year between Algebra 2 and Calculus called trigonometry. That's a whole semester is devoted to that. This is a big topic, and that doesn't cover very much of it. Trigonometry is very important in that. Trigonometry, it allows you to discuss things like, I mean, at the more complicated levels, you can, if you want to study waves, like light is all waves, or sound is all waves, you have to do a lot of trig to look at that stuff and study it. But at kind of an introductory level, it's not nearly that difficult, and it's I don't want to give you the impression that it's difficult in a bad way. Trig's really a ton of stuff that's useful you can do with trig. What we're going to look at today are some simple trig ratios that are based on right triangles. In this section, you could call right triangle trigonometry, and it just comes down to some calculator things you can do based on these trig ratios to do lots of to solve interesting practical problems. Like, for example, if you really wanted to know what the height of a tree was, or a mountain was, or something like that, by just being able to kind of estimate the angle of, from the base of the mountain where you're looking up to the top of the mountain, and having some idea, looking on a map and having some idea how far away you are from the mountain, you could easily, if you had on your phones have calculators on, you could do a little trig equation real simply and find out how tall that mountain is. Trig allows you to do stuff like that where you're not just limited to, as we were talking about last time, you're not just limited to those few special triangles where you know the ratios. It could be any triangle, as long as it's a right triangle. The degrees could be anything. The size of the angle could be anything. Okay? So this is big time stuff, very useful. This will be on the PowerPoint if you want to read it, but we're just talking about trig ratios, or we're going to compare the lengths of two sides in a triangle. So this is the picture we want to look at for this. We've got this right triangle. Obviously, the red side C is the hypotenuse, and sides A and B are the legs. Now, what we do is we set up these trig ratios for each of the acute angles, not the right angle, but the acute angles. And so if we're going to look at, for example, angle A. So let's focus on angle A down here. There are some trig ratios we can set up for angle A. We're going to label all the sides in the right triangle from the perspective of that angle. It's going to change if I go to angle B. Then the way we label the sides would be different. But for angle A, we're always going to break the sides up into the hypotenuse, which is obvious. That's not going to change, is it? The hypotenuse is just opposite the right angle. So that one's fixed. But the other two sides we're going to call the opposite side. Oh, I wish I could move that thing a little bit. The opposite side and the adjacent side. And what does adjacent mean? Next to. Yeah, so if I have a house and you live in the adjacent house, you live in the house next to mine, right? Adjacent means next to. So obviously from the perspective of A, the adjacent side would have to be B, and the opposite side would be the one that you're looking clear across the triangle at, so that would be A, right? Here are the trig relationships, and here's how you remember them. SOH-CAH-TOA. Okay, you'll never forget that. You'll use that a ton from now on in math. SOH-CAH-TOA says it all. That summarizes everything we're doing today. What that says is the sine of an angle, so in this case the sine of angle A equals the ratio of the length of the opposite side divided by the hypotenuse, right? And so it always starts off with, what's the trig function? The first letter represents the trig function, and those are going to be sine, cosine, and tangent. And then the middle letter represents which side is on the top of the fraction. And the third letter represents which side length is on the bottom of the fraction. So the sine of angle A is opposite over hypotenuse, which in this case would be the length of A divided by the length of C. But normally those would be numbers. Okay, they wouldn't just be letters, they'd be numbers. Okay, phones away, phones away. What about the cosine? What do you suppose, without looking over here, what do you suppose the cosine is? Cosine is going to be the ratio of, what do you think? What's the A probably stand for? Well, you have three choices. Opposite, adjacent, hypotenuse, right? Adjacent, sure. So the cosine of an angle is going to be the ratio of the adjacent on top divided by the hypotenuse on the bottom. So the cosine of angle A would be the ratio of the blue side, that's the adjacent leg, right, divided by the hypotenuse, so B over C. Okay? Tangent is going to be the ratio of the opposite side length divided by the adjacent side length. So the tangent of A would be opposite is A divided by adjacent, which is B, so A over B, right? Now, what if we flip this around and we wanted to look at this from the perspective of angle B? Okay, so what if we want to look from the perspective of angle B? What's going to be the sine of angle B? Sine is a ratio of what over what? Opposite over hypotenuse. Okay, so from the perspective of B, what's the opposite side? Yeah, little b, right? So we got B over C. C is always the hypotenuse. Does that make sense? Okay, what's going to be, let's pick another one just at random. What about tangent of B? What would that be? Tangent is over, so the opposite we said was B. What's the adjacent? A, right? Now not C, right? C is not a leg. C is always the hypotenuse. The adjacent one is going to be the leg that's next to, not the hypotenuse. So B over A. Okay? That's it. Now we'll see how that works in some problems. But that's how this whole game works here. So if we want to calculate some trig ratios, let's look at these two triangles. Now we can see that these two triangles are similar, can't we? I gotta fix this up. Give me just 1 second. Okay. So so are these two triangles similar? They are. How do we know that? You're right. How do we know that? Okay, good, because corresponding sides, all three corresponding sides are proportional, right? In other words, if we kind of color code these, the pink ones, the ratio of the pink ones, 17 over 8.5 equals the ratio of the green ones. Equals the ratio of, oh, this thing's off now, I messed this up. It's the ratio of the blue ones, 8 over 4. Right, everybody agree? What's that ratio? In each case, what's it simplify to? 2 over 1, yeah. So 2 to 1. So they are similar, right? Now watch what happens here if we check, what do you think if I calculate the trig ratios of these? Do you suppose that I'm going to get different answers for the different triangles? What do you think? Think I'm going to get the same or different answers? Same, yeah. Watch, you do. Okay, if I take the big triangle compared to the small triangle, everybody see this? It's kind of small. If I calculate sine, right, by SOH-CAH-TOA, sine SOH, right, opposite over hypotenuse. So for the big one, if I'm taking the sine of angle A, right, so we're looking at A, that angle and that angle. Sine of A is opposite 8 over hypotenuse 17, right? What about over here? Sine of A would be opposite 4 over hypotenuse 8.5. Well, if I do the math on those and I turn those into decimals, I can see that I get the same decimals out of those. It's going to work the same for all of them. If I look at all the trig ratios, you know, cosine would be 15 over 17, 7.5 over 8.5, tangent would be 8 over 15, opposite over adjacent, right, so 4 over 7.5. They all end up being the same. That makes sense, though, because trig functions really just depend on the angles that you're feeding them. What we're going to find out is that, you know, when I'm plugging these angles in, I'm going to be putting in numbers typically, right? Usually I'm going to be putting in numbers. And if these triangles are similar, aren't those angles obviously congruent, right? Does that make sense? Because we know that in similar figures, all corresponding angles are congruent, right? It's just the sides that grow or shrink. And so what we're feeding all these trig functions, you feed trig functions angles, and they spit out numbers, right? You always take the sine, cosine, or tangent of an angle. And if the angle's the same, they're going to give you the same answer. In your calculator, when I pull up a calculator here in a second, we're always going to feed, when you pull up any of these trig functions, the calculator's going to expect you to be putting in some number of degrees, for example, right? The size of the angle in degrees or radians, but we'll just use degrees for now. In future years, we'll probably use radians more. So finding trig ratios, no, we already did this. That's fine. We can skip this. I want you to notice here, though, what happens when we look at a 45-90 triangle. That's the stuff we talked about last time. We know these trig ratios. What did we say that the special number was in a 45-90? What was square root of 2 is the number that related the lengths of the sides to the hypotenuse. So if the sides had length 1, right, we'd multiply those by the square root of 2 to get the hypotenuse, right? Well, look what happens if I take the sine and the cosine of one of these 45-degree angles. The tangent's going to be what? If I look from the perspective of this 45-degree angle down here, let's label the sides. What's this side going to be over here? Is it going to be O, A, or H? O. This is obviously H, so that must be adjacent, right? So if I look at the tangent, the ratio of opposite over adjacent, that's just 1, isn't it? 1 over 1. Okay? What about the other ones? If I take the ratio of sine of 45, that's going to be 1 over the square root of 2. If I take cosine of 45, I get 1 over the square root of 2. I can't leave a radical on the bottom, though, right? So I'd multiply top and bottom by the square root of 2 to give me a 2 on the bottom and a square root of 2 on the top, right? And so we always know then, this is one when we go on later, future years and study trigonometry, you're going to be memorizing some of these really common sines and cosine, these values. Sine of 45, you'll memorize this, is simply the square root of 2 over 2. Okay? So is cosine 45, square root of 2 over 2. For now, you just put it in the calculator. Or just use the triangle ratios that you know. For a 30, 60, 90, same kind of deal. Let's take the 30-degree angle, right? If I start down here with the 30-degree angle, if I look at the sine, that would be, this is the opposite side, right? Adjacent and hypotenuse. And we know that if the short leg has a length of 1, we got 2 magic numbers, remember those? Multiply by 2 to get the hypotenuse, by the square root of 3 to get the long leg. And so I could come up with all these trig ratios too. The sine of 30 would just be opposite, which is 1, right, divided by hypotenuse, which is 2, so 1/2. Okay. The cosine would be adjacent, which is square root of 3 divided by hypotenuse, which is 2, so square root of 3 over 2. And then the tangent, opposite over adjacent, 1 over the square root of 3 multiplied by square root of 3 over square root of 3. This one we don't really use that much. But these two are very common. Those are ones you're going to, when you study trig later on, you're going to get to know 1/2 square root of 3 over 2 and square root of 2 over 2. Those numbers come up constantly. Okay. All right, so you get the idea. We don't have to do another one of those. Let's just take a look at how we actually use this on a calculator. So if we want to find for a 74-degree angle, sine, cosine, and tangent, what do? Well, you can't do this without a calculator. You have to have a calculator. Let me show you how you do this stuff on your calculator. There's a couple settings you got to get right, or you'll get. One of the most common ways people make mistakes is they have their calculator in the wrong mode. There's 2 modes on a calculator: degrees and radians for trig, and you got to always make sure your calculator's in the right mode. Most common mistake by far on trig tests that I've given is that's it. Really. Okay, so. Okay, so if I want to do this, if I want to take, let's say, the sine of 74, where do I go to get sine? On here. The button, right there. S-I-N. That's our shortcut for sine. And then I just need to put the angle in there. But first, I got to check the mode. So I go to mode, and see right now, if you go down to the third line down, you have a choice of radians or degrees. Well, I'm in the wrong mode. I need to be in degrees. Whoops. So I got to go down to degrees, turn it to degrees, hit enter. Now I can quit. Okay, now I can go over and put in my 74. And that's it. That's the answer. If I want to get cosine, same deal. Cosine 74, close the parentheses. There it is. Tangent. TAN is tangent. So that's how you're doing it. And all calculators, and your phones will have these too. So I would say all the calculators on phones will, but it's easy to find a free one that does if you don't have one. Okay, so a couple things about sine. The sine and cosine are always going to give you numbers back that are less than that. Okay, they could be negative, but they're not going to be as long as they're acute angles, they'll always be numbers between 0 and 1. So if they're numbers, if taking the sine of an angle between 0 and 90 degrees, always get numbers back between 0 and 1. Tangent won't always be that way. But sine and cosine will. One other trig identity, last thing. Well, actually two of them. Okay, this is stuff, we're not going to do a lot with this now. And I'm just showing you this because I think it's useful to see some of these things more than once in your life when you're going to study. Phones away. Put those away. Oh, you don't have that? Yeah, put it away. Thought so. If you are going to see this again later. This is the Pythagorean theorem for trig identities. What this is saying is that the sine of a squared, if I square that number plus the cosine of a squared, that's always equal to 1. Okay, that's a really common trig identity. It's something that you'll see over and over again in the future. Just want you to see it once. We're not going to do a lot with it, honestly. I might throw in, 1 or 2 challenge problems that make you just kind of explore that a little bit. We're not going to do a lot with that one. This is also a really useful one. The definition of tangent. There are 6 total trig functions. We're only looking at 3 of them now, sine, cosine, and tangent. But there's also secant, cosecant, and cotangent. And those will come up later. All of those trig functions, all 6 trig functions, can be written in terms of the most basic ones, which are sine and cosine. Okay. And so tangent, remember, tangent is always sine over cosine. It's the ratio of sine divided by cosine. Once again, not a huge issue for us now. We're not going to do a lot with it this year. But as you go further on, that's going to be another one that's going to be really important. Like in trigonometry and pre-calculus and calculus, that's a big deal. We use that all the time. So just so you can see it. All right. Last but not least, let's see. How could we solve a real world problem like this? So let's say that we want to measure the height of this big tree, right? This is not hard to do with a little bit of trig. If we can measure this angle, which honestly isn't hard to do, I mean, all you really would have to do to measure that angle would be if you just had a single, not to carry a protractor with you, but if you did, you could easily measure that angle. But you could also measure the angle. You could estimate pretty well what the angle is based on knowing what 45 is, and you're going to get a pretty good estimate. So let's say that we know that this angle is 59 degrees. We can measure that or make a good estimate of this angle as being 59 degrees. And it's pretty easy for us to make a linear measurement, a tape measure. Right? We can know how far we are away from the trunk. How could we use trigonometry here if we know this angle to be 59 degrees and we know the height to be, or the distance from the tree to be 45? Any idea how we could set something up here to make a good, accurate estimate of the height of that tree? What do you think? So from the perspective of this angle here, let's start off this way. Let's think of this in terms of maybe our trig ratios. So here's the angle we're looking at, right? How would we label the sides? What would be what here? It's a right triangle, isn't it? Because the tree is standing straight up and down and the ground is flat, let's say, right? What sides go where? Okay, so the 45 feet would be adjacent, so we'll call that A. Okay, what else? Okay, so the height is going to be opposite, good. And then this is hypotenuse, but the hypotenuse is really, we don't want the ratio with hypotenuse, do we? Because the hypotenuse is not the measurement that we're trying to estimate. We don't really care about that distance, and we can't measure it, right? We've measured the horizontal distance, and we want to find the vertical distance. So what's the SOH-CAH-TOA trig ratio that's going to relate those two things? The thing that we're looking for, which we'll call x, let's say, and the thing that we know, which is 45. Which one of those works? Just do this at the top of your paper when you're taking a test, right? SOH-CAH-TOA. Which one do we want? First, second, or third? Third. Well, which one?
Third.
Probably the third, right? We don't want the first because we don't want hypotenuse. So we don't want that one, and we don't want that one. We want the one with no hypotenuse. So that's which one? What's that trig function called? Tangent. Okay. So we know that the tangent of our angle, which is 59 degrees, right? Equals what over what? What's that going to be in terms of our picture that we drew? Okay, yeah, opposite we said was x, that's the unknown. I think we call it height too would be fine, but we'll just call it x, over adjacent, which was 45. Okay, now algebraically, this is a little weird, but algebraically, how do we isolate that x? What's the one thing I have to do to isolate that x? What do I have to do to get it by itself algebraically? It's being divided by 45. How do I undo dividing by 45? Say it again. Multiply by 45. Okay, so all I've got to do here is multiply both sides by 45, and the 45s will cancel. Now, this looks a little weird, and sometimes people get real, freaked out by the fact that what do you do with that tangent? Can you multiply by a tangent? Absolutely. A tangent is just a number. When I put this into my calculator, the tangent of 59, it's just going to spit out some weird decimal number, right? So this whole thing, and this is how you got to think as a mathematician, this is how you have to think about this stuff. This whole weird creature right there is nothing more than a number, just like 1 or 2 or 3 or 4, but it's one that your calculator's going to give you. So I'm just going to multiply 45 by this weird number that I'm going to get from my calculator. And that's my answer, right? If I do that, if I pull up my calculator, my trusty calculator here, and see what I get, I just go 45 times tangent of 59. And I'm just multiplying two numbers. And my answer is 74.9, so it's about 75 feet tall. And that's a pretty good estimate. Okay? Make sense?
Mm-hmm.
So that's what this is. This is really used a lot. People that do surveying would be constantly using trigonometry. Those guys that get out there with a little, they survey property and things. It's all based on trig. Okay. How much time we got? A little bit. Let's be done with this.